Okay, next is the effects of momentum thickness. Okay, this is momentum thickness. So another measurement of boundary layer thickness is a momentum thickness, or commonly known as delta double star or theta. Okay, the momentum thickness is defined as the loss of momentum flux per unit weight divided by rho u square due to the presence of growth of boundary layer. So this is the general equation of momentum thickness. Delta or theta is equal to integration of u divided by u, big U, small u divided by big U, 1 minus small u divided by big U dy. So the momentum thickness for lamina is theta divided by x is equal to 0.664 divided by square root of Reynolds number. Okay. So momentum thickness is defined as a loss of momentum due to presence of growing boundary layer. Okay. So now you can see there is a two illustration. On your left side is illustration of unsteadiness of a turbulent boundary layer. The thin wavy black line are instantaneous profile and the thick blue line is a long time average profile. So it shows that unsteadiness of turbulent. On the right side, it shows a comparison of lamina and turbulent at the flat plate boundary layer profile for non-dimensional boundary layer thickness. So you can see the graph on the right side is delta y divided by delta. So this is the boundary layer. So this is u divided by u, means the non-dimension of the velocity. So when the velocity increase, you can see the lamina graph show the effect of boundary layer is higher than the turbulent. Turbulent once started from for example 0.5. Okay, 0.5. So then the turbulence start to increase. But there when we take it what we call it gradient, the gradient of lamina is lower than the gradient of the turbulent, because the turbulent shows more stiff. Just start, then it directly increase. Okay. Okay, this is a turbulent flat plate of boundary layer. This is for turbulent. Just now, the example more on lamina. So this is turbulent flat plate boundary layer, which is this is the formula of boundary layer. Okay, which is delta x divided divided by delta x. For lamina, you can use 4.91 divided by square root of the number. But for turbulent, you can use either A or B. What is A, what is B? The A is obtained from 1/7 power law, but B is obtained from 1.7 power law with empirical data for turbulent flow through a smooth pipe. So this is more combining with the empirical data of turbulent flow in the smooth pipe. Okay, this is the general of turbulent. The A is general turbulent of power flow. Power 1/7 power law. Sorry. So when you have equations, you need to calculate first is the lamina of turbulent by using Reynolds number. So from here you know lamina or turbulent. Then number 2 is, for example, here select the best formula. If the question asks you boundary layer, if lamina, you use this one. If turbulent, we use the second one or B1. Okay. Okay, or the second displacement, delta star is 1.72 divided by square root of Reynolds number. But for turbulent, you have 0.02 divided by Reynolds number square root of 1/7. And also, another one is 0.04 divided by 1/5. Okay, for a number. So there is a formula of momentum thickness, and last one, local skin friction coefficient. So you need to remember, understand this formula. Then we will ask you by something like not similar, something like the same concept. You need first to calculate laminar or turbulent. For example, you calculate to become turbulent, but you use the formula of laminar. The rest will be wrong. So that's why it's important for you to know how to calculate the real number. Like previously, this is just an what we call it reminder. If, for example, this is, be aware, right? In this question, I've put 50 centimeter diameter and 50 centimeter length. For example, I put it here is 55 centimeter diameter and 50 centimeter of length. One thing, based on my experience, the Renault number, not everybody will have, not everybody, out of 100%, maybe 20% will have wrong. Because most of people are confusing to use the D diameter of the length, or the length. Right now it's easy, when we put it 50, because we know Renault number formula is, in this case, Vx over, no. Okay, V is no problem, this one also no problem, X is a problem. Some people will use 50 centimeter, some people will use 55 centimeter. So in this case, the correct one is 50 or 55. In this case, anybody? 55 or 50? The X.
Not sure, doctor.
Why not sure? Okay, Shahirul said 50. Okay, one said 50. 50 or 55? You see now still say 50. Okay, this is. So in this question, previous session we give it similar, 30 and 30. So everybody select 30. You won't be wrong. Okay. Interesting. 50 or 55? Shannon said 55. Okay? Okay, what I want you to do, okay, everybody try to find when to use 50, when to use 55. I means that, where is the questions? Okay, for Renault number V, in this case Vx divided by nu. So do you use the length or do you use the diameter? 50 is diameter, 55 is the length. So in this case, 50 or 55. So I want each of you to try to find the answer 50 or 55. Okay? Then we will discuss. Okay. When to use? This is important, eh? This is important because Renault number you will use in most of your questions. Not only questions, you will use in your entire syllabus or entire degree. So you need to understand when to use length, when to use diameter. Okay. So try to find back, okay, your task to understand for your understanding. Okay. So I want you to find, instead of I'm telling, I want you to find. Everybody find the answer. Okay, because this is important. When I give you this type of questions, then you will confuse. For example, the answer is A, which is, for example, okay, we have 30 and 35. For example, actually the correct answer is 30, but you use 35. Your real number is different. You need to remember the effects. For example, this is an example. When you start, okay, you have A or B option. A is 30, for example, B is 35. When you calculate real number, When you use 30, you will get laminar. This is an example. If you get 35, you will get turbulent, for example. You just imagine what happened to your answer. So, AP people will use the formula of, for example, displacement equivalent of laminar, delta star laminar. The B people will use delta star of turbulent. At the end of the day, okay, this is different answer, this is different answer. For example, the correct answer is 30. Only these A people only get the answer. The B people will get half of it because of maybe the method. So you just imagine, due to these effects, understanding what to use, then it will, from the Reynolds number effects, then it will lead to the other effects. So this is normally in the test we will test you. Okay, why? Because we want you to understand. We want you to be confident to understand, to use as simple as this one. Real number, to calculate real number, you want to use a 30 or 35. You want to use the D or the length. So my advice, this is I'm telling, because finding yourself is better understanding rather than just telling. So I want you to find back and find the answer for your own understanding. Okay? So you can discuss with your friends what is the correct one. You can find the books where to use D is diameter, when to use D is length. Okay? So I continue the next your task for your understanding. Remember, the test won't be directly straightforward. Okay? Because we want to test your understanding like the first test. Especially I think first and second is very easy, straightforward. The third and fourth, a lot of you cannot answer, but due to we give you a chance, the marks is quite high. For me it's very high, because your marks, frankly speaking, a lot of additional marks to get your marks. So especially question number 3 and 4 is quite difficult, and we give you some because this is the first open book test. So this is the difference between open book and what we call it, closed test. Closed book test is directly. Open book test, the question are not directly. As simple as definition also, we are not, just we try to make it not directly. Like for example, the first test, non-Newtonian and Newtonian. Some use, most of you said pseudo fluid. Pseudo is the type of fluid of non-Newtonian. Of non-Newtonian fluid. Non-Newtonian fluid, correct. But because I put it X there, some of you are not discussing about the Newtonian and non-Newtonian. So that type of open book type question. And you need to remember, due to MCO, due to the online of the class, we will do the question for the second test and final is open book test questions. So it's not a direct questions. Okay? So for the second test, you can open your book, but the question will be based on your understanding. And the main enemy for you is time. Okay? So this is a reminder. Okay? So as simple as that questions, how many of you will find the correct answer? It depends on your understanding. Okay? As simple as these questions. Okay? So we continue back. Okay, just now is a turbulent flat plate boundary layer. The next is boundary layer with pressure gradient. Okay, you can see there is a picture A and B. Picture A is boundary layer developed along the fuselage of an airplane and into the wake. If you can see here, there is a grey color here. This grey color. This grey color shows the boundary layer of along the fuselage. Okay. Okay. The second one is boundary layer growing on the wall diffusion. Boundary layer at the wall. Okay, you can see the grey color. So this is boundary layer for non-zero gradient. Non-zero gradient means that there is no additional of pressure gradient. So it's a naturally when you have a aeroplane, so there will be a boundary layer effects on the body of the wall. Okay. So boundary layer with pressure gradient, there is a favorable pressure gradient and also adverse pressure gradient. Okay, the favorable pressure gradient is the boundary layer in such acceleration flow is usually thin. Okay, the character is thin, hugs closely to the wall, and therefore is not likely separate from the wall. Okay. The second one is adverse pressure gradient is a boundary layer usually thicker, does not hug closely to the wall, and is much more likely to separate from the wall. Okay, so you can see here the grey color, we call the grey color is favorable. The grey color, okay, in terms of favorable gradient is thin, it's not likely separate from the wall, so it's something like the grey color. Okay, but the adverse is thicker and much more likely to separate from the wall. So there is another adverse pressure gradient. So it happen is far from the wall. Another one is favorable pressure gradient at the wall. Okay. This is the example of boundary layer separation. Okay, boundary layer separation in region adverse pressure gradient. So the A1 is airplane wing at moderate angle of attack, B at the high angle of attack, and C is wide angle diffusion in which the boundary layer cannot remain attached and separate on either side. If you can see here, okay, this is a wing. Okay, this is a low angle of attack. Angle of attack means that, okay, your original flow of wing is 0. This is what we call it, 0 angle of attack. So then we increase a little bit here the angle, so there is a, for example, 4 degree of angle of attack. So this is the moderate angle of attack. When we do the flow streamline, there will be a flow separation point happen. Means that the flow will go smoothly. Okay, until one point. At this point, the flow start to be, we call it recirculation start to happen here. So this point we call it as a separation point. The moment of the flow start to be recirculation. Okay, when we increase the angle of attack, the separation point will be increased or will be near to the leading edge because of the flow obstacle of this effort. So the flow will be happen of negative pressure here, high pressure here. So there will be a recirculation happen here. Okay. So this is the effect of separation flow. This is not good. The separation flow will make this area uncertainty. That's why your flow are not smooth. What happen is there will be a lot of increase your drag here or something like here. So when you want to take off, there will be a separation flow happen here. So you need to, that's why a lot of research try to redesign the airfoil in order to reduce or to make sure the separation flow happen at the end of the wing. Okay, so in this case, okay, the boundary layer remain attached to the entire lower of body airfoil but separate somehow near the near rear of the upper surface as sketched. So the closed streamline indicate the region of circulation flow called separation bubble. So this here we call it as a separation bubble. This one is separation bubble. This area. This is separation point. Here is we call it separation bubble. Here we call it separation bubble. Okay. Okay, this is the comparison of boundary layer profile shape as function of pressure gradient. Okay, when pressure is favorable, so the profile is something like this. Okay, focus on here. Okay, so this is a normal condition. When the pressure gradient is zero, okay, means zero started from zero. This one actually is not started directly from zero, but here, for example, is started from zero. The pressure gradient will be a little bit increased. Okay, so the flow of the boundary layer will be increased. Okay, the C is mild adverse, means that your boundary layer effect start to be have a mild adverse. So you can see the profile will be directly diverge towards. For example, here is your boundary layer. Okay, so you can see the profile change. Then the third one is critical adverse, means that the diversion start to be increased at this point. And the last one, when the boundary layer is effect is higher, what will happen is there will happen of reverse flow happen. Okay, so reverse flow is large adverse, which is inflection point are indicated by the blue color. Okay, and wall shear stress is sketched for each, means that this reverse flow happen. So that's why the boundary layer is important to understand. When you have a higher boundary layer, something like that, so there will be one point of reverse flow will happen. Okay, now this is example of CFD calculation of over a bump. Okay, the A1 is solution of Euler equation of the streamline plotted no separation flow. So assume there is no separation flow, so you can see the flow will be smooth. So the flow smooth, this all everything smooth from the bump area, means favorable area and also adverse. The B1 is laminar flow solution, flow separation on downstream side of the bump. So means, for example, we go for, there is a at this area, something like here. Okay, going down, so the flow going down, but there is a separation point happen here. So the moment there is a separation point happen, the flow in this will become a reverse flow, or we call it this area or separation bubble. Okay, the C close up, when we zoom it of the streamline near the separation point, so there is a point here approximate, and also the reverse flow to be this is more close up. So in terms of vector, this is the what happened here. You can see the arrow, instead of the rest, the arrow will be straightforward. Here there is a arrow start to be recirculation. This one is, we want to reduce the effect of reverse flow. The reverse flow will, especially in airfoil, will make the flow, will give you a lot of drag. It's not a good thing lah. So this is reverse flow. We try to reduce this reverse flow by changing, for example, the design of airfoil or something like that, in order to see separation point to be reduced at the end instead of on the airfoil. Okay, you can check in chapter 9. I think there is more detail on this one. Okay, this is boundary layer. Boundary layer approximation. Okay, boundary layer approximation is only a good as the outer flow solution. If the outer flow is significantly altered by the flow separation, boundary layer approximation will be erroneous. Okay, turbulent flow layer are more resistant to flow separation than a laminar boundary layer exposed to the same adverse gradient. Okay, we go by example. Now we learn a little bit of theory. Now is example. So there is an A-plane wing with 7.62 meter span. Okay, and 2.13 chord. Estimate the drag on the wing two side, treating it as a flat plate and flight speed of 89.4 meter per second to be turbulent from the leading edge. B is determine the reduction power that can save it if the boundary layer control device is installed on the wing to ensure lamina flow over the entire wing surface. So now we take it as the density is 1.1 kg per meter cube. Then kinematic viscosity is 1.3 times power of -5. So this is the concept of the effect of turbulence boundary layer. Okay, this is the formula for CD, coefficient of drag for lamina. This is coefficient of drag of turbulence. Okay, so in order for that, we need to calculate first is what is estimate the drag. So we know that in order to calculate the drag is FD. The formula of FD is 1 over 2 rho AV squared. Okay. Okay. So okay. Meeting will end 5 minutes. Okay. Okay, I will finish in 5 minutes. Then we will re-enter back for your presentation. Okay. So in this case, we need to find the FD first. So this is the formula of FD. We know that 1 over 2 rho AV squared times the CD. CD is coefficient of drag. First of all, as I mentioned, you need to calculate the Reynolds number. So in this case, your V is 89.4 for your V. Then for your length is your chord. Okay, what is chord? Chord is, this is your wing. Okay, this is your, for example, here to here we call it as span. I think in previous chapter or in chapter 9 will be. So this one is chord. Okay, so the flow is from this side. The moment the flow is from this side, you need to know your D or your X will be the length, the chord one, because of what is easier is, okay, this is your flow, what which length, what we call it, cut the flow, will flow here. So this is your chord. So you take chord, you cannot take span. Okay, span is if the flow is from here, for example, then your length is span. Okay, now your flow is from this area normal, your length is chord. Okay, so here your length is 2.13. So your nu is 1.3, kinematic viscosity 1.3 times power -4. So you get 1.2 times power 7. So we know directly this is a turbulent flow. So because of this turbulent flow, number 1, you get it turbulent. Then you should use this equation number 2, because of turbulent flow. Okay, correct?
Yes, doctor.
Okay, correct kan? Okay, so you use the coefficient of drag of turbulent formula